One other piece of information you can get is magnetic property. Okay. Magnetic dipole moment. Okay. If you recall, we said that psi is equal to a function of r times a function of theta and phi, and a function of theta and the function of theta and phi, we said, is a spherical harmonic. Because of this, we could say that your electron in an orbital has a well-defined magnitude of the angular momentum. L squared of psi is just going to be L times L plus 1 h bar squared psi. Because as far as the L squared operator is concerned, if you remember, it doesn't depend on r. It only depended on theta and phi. In fact, when we talked about the L squared operator, we mentioned this when we did the particle in the sphere. So as far as the L squared operator, your r will just factor out. So you get the same eigenvalue as for the spherical harmonic, just the spherical harmonic. Okay, so the magnitude of the angular momentum is just going to be square root of L times L plus 1 h bar. It's this one. This is h bar. And we also say that if m is well-defined, the quantum number m, then the z component of the angular momentum is also well-defined. L sub z will just be equal to m h bar. Okay? All right. Since you have a charged particle going through some kind of circular motion, the orbital motion of an electron generates a magnetic field. Okay? So the magnetic dipole moment that it generates is given by this formula right here. Magnetic dipole moment vector is just equal to the charge of the particle divided by 2 times the mass of the particle. The mass is the mass of the electron in this case, times the angular momentum vector. Since the charge of the electron is negative, that's negative 1.602 times 10 to the negative 19 coulombs, or negative E, then you can say that if this is the L vector, the angular momentum vector, then the dipole moment vector will just be pointing in the opposite direction. Okay? Now, so since the angular momentum is quantized, the magnitude of the angular momentum is quantized, then the magnitude of the magnetic moment vector must also be quantized. So what would be the allowed values of mu? Well, let's see. Allowed values of the magnitude of this vector is going to be equal to, okay, negative E over 2 times mass of electron times the allowed values of L, which is square root of L, L plus 1 h bar. Okay? When we do this, you get negative E h bar over 2 times mass of electron square root of L, L plus 1. Since we're only taking the absolute value, you don't have to worry about that negative sign right there. Now this term right here, E h bar over 2 times the mass of the electron, that's known as the Bohr magneton. Okay? E h bar over 2 times the mass of electron, and this is the value for that, 9.724 times 10 to the negative 24 joule per Tesla. So that's just going to be equal to mu sub b, the Bohr magneton, times square root of L times L plus 1. Okay, so let's answer this question. What is the magnetic dipole moment due to the motion of an electron around the nucleus if the electron is in the s orbital? Well, for an s orbital, L equals 0, so the magnitude of the orbital angular momentum is 0. 0 plus 1, square root of that, times h bar is 0. So therefore, the magnetic dipole moment is also going to be equal to 0. So an electron in a 1s orbital will not be magnetic. It will not generate a magnetic dipole. What about this question? How many possible orientations are there for the magnetic dipole moment due to the motion of an electron around the nucleus if an electron is in a d orbital? Well, if it's in a d orbital, then there are 5 possible orientations for your angular momentum vector corresponding to m equals +2, +1, 0, -1, and -2. So your L vector could be that pointing there with a z component of 2h bar. So that's m equals +2. And so if that's the case, then your dipole moment vector will be pointing in the opposite direction. Okay? And you can have m equals +1. Z component is h bar. Or you can have m equals 0. Oops. M equals -1. Or m equals -2. So there's 5 ways. 2L plus 1. Okay, it's 5. 2 times 2 plus 1. It's 5 different orientations for the magnetic dipole moment. In other words, what you can think about the electron as though it's like a little tiny magnet. Okay, so where this mu vector is pointing, you can say that's where the north pole of the magnet is. So you can imagine the electron as like a little, because of the magnetism that it generates, it's like think of it as like a bar magnet where the north pole is pointing this way. This way. Okay. Oops. So let's take a look at this question. How many ways can the magnetism generated by the orbital motion of an electron in a 3p orbital be oriented? The answer to this would be 3. That would correspond to m equals +1, 0, and -1. So what experimental evidence do we have for these magnetic properties? That thing is called the Zeeman effect. Okay, so this is the evidence that we had that the angular momentum of an electron is quantized. Zeeman effect refers to the splitting of the spectral lines when you subject the atom to an external magnetic field. So if the atom is behaving like a magnet, then if you subject it to an external magnet, it should react. Okay, what did we learn in grade school? If you have opposite poles attract, like poles repel, right? So if you were to subject, okay, so let's say you have an external magnet. This is the north pole of your external magnet pointing that way. That's your positive z-axis, let's say. And if your magnetism from your electron is oriented this way, there's the north pole, the south pole, there's going to be a repulsion between the electron or the atom and the external magnet. And so this would subject the electron to, we say, a higher potential. It would make the atom have a higher potential energy as opposed to when the south pole is the one that's pointing towards the north pole. Okay, so the 2p plus 1 and the 2p minus 1, for example, would now correspond to different energies. We say the degeneracy of the energy for a given sublevel will be lifted. The energy will now depend on the m quantum number in the presence of an external magnetic field. Okay, so if the remember -r times z over n squared, that's the energy of your atom without, or your electron without the external magnetic field. In the presence of the external magnetic field, you have to add a term to your Hamiltonian, and so that leads to an extra term in your energy due to the potential energy of interaction between the external magnet and the magnetic dipole moment that's generated by the orbital motion of the electron. So it depends on the quantum number of m here. Mu sub b here is your Bohr magneton. B is the strength of the external magnetic field. Okay. So what would be the energy level diagram for n equals 2? When it's subjected to an external magnetic field. Then in this case, you're going to have, instead of 1, 2, 3, 4, 5, okay, n equals 2, you're going to have 2s, right, and 2p, plus 1, 0, -1. Here m is 0, okay. all those 4 orbitals would correspond to the same energy level, E2, without the magnetic field. In the presence of a magnetic field, okay, your 2s and your 2p0 will be unaffected, but your 2p plus 1 would be higher in energy, okay, and your 2p negative 1 would be lower in energy. And by how much? This difference right here is equal to mu sub b, Bohr magneton, times the strength of the external magnetic field. So the stronger the external magnetic field, the bigger the splitting of these energy levels. So if there's a splitting of the degeneracy, if you have more energy levels, what happens to, instead of just one spectral line, you're going to have more than one spectral line. Your spectral line in the presence of a magnetic field will split. Okay? In the presence of an external magnetic field, into how many lines does the 2p to 3d spectral line split? So if you remember, transition from the 3d orbital to the 2p orbital, okay, is allowed. Delta L equals plus 1 there. So if you remember your selection rule, delta L is plus or minus 1, and delta M is 0 or plus or minus 1. So normally all the 3d orbitals and all the 2p orbitals would be in the same. All the 3d orbitals will have the same energy, they're degenerate. All the 2p orbitals will have the same energy, they're degenerate. And so you're just going to see one spectral line. Delta E from 3d to 2p is just going to be one possible value. But what happens due to the magnetic field? This 3d will now look like what? 5 different levels. This is for m equals 0, m equals plus 1, m equals plus 2, m equals negative 1, m equals negative 2. Your 2p will now be 3 levels. You have 2p0, 2p plus 1, and 2p negative 1. Okay? So your m equals 0 levels are not shifted by the magnetic field, but the negative m's and the positive m's are shifted. So instead of just this one line, you're going to get extra lines. So you can have from m equals 0 to m equals negative 1. That's allowed. Delta m here is 0 or plus or minus 1. So this would be a bigger delta E. So instead, so if you look at, instead of just that one spectral line from 0 to 0, okay, you can go 0 to negative 1. So if this was wavelength right here, okay, from 0 to negative 1, that would be a bigger delta E. That would show up in a shorter wavelength right here. Okay, so this is 0. Okay, usually you write the upper quantum number on the right and then draw a left arrow. So 0 to negative 1 would go there. What about 0 to plus 1? That's a smaller delta E, so that would be at longer wavelength. So that you'll see a spectral line appear on the right for transitions from 0 to plus 1, and that's what happens in the presence of external magnetic field. That's not the only thing you'll see. What else do we see? You go from, let's see, from negative 1 to negative 1. Where would that show up? Same here. Negative 1 to negative 1, this same. That's unshifted. Okay, but you can you go from negative 1 to 0? That's allowed. Okay, and that would be shorter. I mean, smaller delta E. That would be a longer wavelength. So this would also correspond to a transition from negative 1 to 0. Okay. Negative 1 to plus 1, that's not allowed because that would constitute a delta M of 2, okay? And so if you work this out, for all the possible transitions, you'll find that you're only going to see, you're going to see 3 lines. You would expect to see 3 lines. And here's the website where you might see that illustrated. Let me pull up that website. just do a search for Z-man effect hyperphysics. It's a website in Georgia State. And this is what happens. This is a summary of all the transitions from 3D to 2P. Okay? And the arrows here show you the transitions that are allowed. So instead of just one line, in the absence of a magnetic field, with a magnetic field, you see 3 lines instead. Okay? Notice that from m sub m equals 2 in the 3D, you can go to m equals plus 1. Okay? But you cannot go to m equals 0. It's not allowed. Delta m equals 2 there. Okay? From m equals 1, you can go to m equals 1 or m equals 0, but you can't go to m equals negative 1. Clarify that. So from m equals 1, you can go to m equals 1, 1 to 1, and you can go, okay, and you can go from m equals 1 to m equals 0. But you cannot go from m equals 1 to m equals negative 1. That's part of the selection rule.